Alright, this video is going to be on all the polar parametric equations for your exam, so it's going to start here with number 1. So which type of equation would describe the following parametric equation? Now, in order to figure out what type we have, we're going to need to eliminate the parameter so we can get it into rectangular form. So luckily this is a pretty simple one. It's just x is equal to t, so we don't really have to do much to eliminate the parameter. We just plug in x for t. So we're going to get y equals 3x plus 2. Now it says, which type of equation would describe this? This one would be a line. So that's number 1, which is a line. Number 2, we're going to do the same thing. Which type of equation would describe the following parametric equations? We're going to eliminate the parameter yet again. Now this one we actually have to solve for t. So I'm going to take this one. It doesn't matter which one you choose, but typically we'll start by eliminating the parameter in the x for the x equation. So we're going to solve this for t. So I'm going to add 3 to both sides. So x plus 3 equals 2t. I don't know why I wrote a y there. And then I'm going to divide by 2. So this is our t equation for a horizontal component. And now I'm going to take that and I'm going to plug it in up here for t. So that gives me y equals 5 minus 3 to the x plus 3 over 2. And again, I'm going to zoom in here a little bit so you can see a little bit better. We distribute, so we get 5 minus, and as we do this, this would be, let's see, 3x minus 9 all over 2. Again, if you're trying to simplify, you're probably going to want to separate that 2 in that fraction. So I'm going to get 5 minus 3x over 2 minus 9 over 2. You can probably see at this point this is a line. In order to simplify this, though, I'm going to combine my 5 and my 9 halves. So I'm going to subtract 5 and 9 halves to leave it as a fraction here. Oops, I meant to do it like this. I'm just going to go 5 over 1 minus 9 over 2. Now if you want to get a common denominator of 2, then this would now be 10 halves minus 9 halves. So that's just going to equal 1/2. So when you put all this together, we're going to have negative 3x over 2, or negative 3 halves x, if you want to do it that way. And then we have this plus 1/2. Again, yet another line. So a couple different variations there, but we have a line and a line for 1 and 2. Alright, and moving on to number 3. This one I'm just saying eliminate the parameter for the graph. So this one we're going to do the same thing we just did. We're going to add 1 to both sides. So that's going to be t equals x plus 1. I'm going to take this and I'm going to plug it in for t in my second or my vertical equation here. So I have y equals x plus 1 quantity squared plus 1. So what we need to make sure we don't do at this point, we don't just distribute that square. We have to FOIL this out, which is basically distributive property. So we're going to go x plus 1, x plus 1 plus 1. Alright, so that's x plus 1 quantity squared. So again, just part of the simplifying process. Now again, if you leave it in this form, I guess that's fine. It just depends, if it's multiple choice and it does have it written out in standard form, then we're going to need to do that too. So I want to go through that process so you're prepared either way. The vertex form is given above here. But this is going to be x squared plus x, 1x plus 1x is plus 2x plus 1 plus 1. And finally, we get x squared plus 2x plus 2. And that is eliminating the parameter, number 3. Alright, and number 4, we're going to find at least 3 other polar coordinates to describe that given point. A couple easy ones we can do. Obviously we can do 30 degrees just by converting that to degrees. We can also go in a clockwise direction, so once I go to the right 2, I can just kind of go around this way. If I do that, that's going to put me 1 away from 360. And in terms of pi over 6s, I'd be 1 pi over 6 away from 360. So that'd be 2. Let's see, yeah, okay. So that'd be 2, and then 11 pi over 6, but I'm going in this case a clockwise direction, so negative 11 pi over 6, and that's just a couple easy ones. Some other ones that we can do as well. You can also go negative 2, so you can go this way, and we can go in any direction we want from here as well. So if I go in a clockwise direction, so again I'm going negative 2 now, but if you're going a clockwise direction, you're going 180 plus 30 degrees. So 180 plus 30 is again 210 degrees. You can also go negative 2 and do that as 7 pi over 6. Again, there's a lot of different options here. I'm just kind of giving you a few. You can also go, in this case, in a clockwise direction. Actually, I'm sorry, that other one. No, we're good. I went the right way. This one's going to be clockwise, so I'm going to have negative angles. So if I'm doing negative angles, again, I'm at negative 2. But again, I'm going in a clockwise direction, so that's going to be 5 pi over 6. Or you can go negative 2, and that's going to be 150 degrees. So I just gave you a bunch of different options. You kind of pick and choose which ones you'd like to use there. At least 3, but you have to kind of know all of them because it is multiple choice, so just make sure you're prepared either way. So next up is going to be number 5, converting rectangular points to polar form. So we have our point, again, right now in rectangular form. A couple things we want to know as we're doing our conversions. For one, we know that we want to get this in terms of r. So r is equal to the square root of x squared plus y squared. And we want to get our theta. So remember, tangent of theta is equal to y over x. So we can also say that tangent inverse of y over x is equal to theta. So we're going to use these equations to do our conversions. Starting with r, that is equal to, again, the square root of x squared, so negative 4 squared, plus y squared, so 4 radical 3 squared. So that's going to be equal to the square root of 16, and then we have here 16 times 3. So when we multiply that out, that's going to be 48, and then we have 48 here and 16 here. So that's 5864. So we end up with 8. That's going to be our r value. Next up is our theta value, and remember, theta is equal to the tangent inverse of y over x. So 4 radical 3 over negative 4. Now these cancel, and you basically end up with the tangent inverse of negative radical 3. So if you're studying that unit circle, you know how the angles work. This is, again, stuff we've been doing all year, so it helps. We know that when we're doing radical 3, it kind of goes both ways. One's positive, one's negative. But this point right up here, the tangent value at 60 degrees, that's at radical 3. Remember, the tangent value at 30 degrees is radical 3 over 3, and the tangent value at 45 degrees is 1. So all we're doing is we're going negative. So we're going down. And again, you want to pay attention to what quadrant you're in, and I'll talk about that in just a second, but this would be negative radical 3. Now notice you're not in the second or the first or the fourth quadrant in this case, because you're going left 4 and then up. You're actually in the second quadrant. So we take that same concept and we just move it over to the second quadrant. So again, as we're doing this point right here, again, if you're in the second quadrant, this is going to be radical 3 over 3. In this case, it's negative radical 3 over 3. And our point up here, not that we need that other one, but this point is the one we do need, which is negative radical 3. And see how it's a reflection right there. So once you have all that information, again, all you're doing is you're trying to find that angle. That's theta. Okay, so in this case, theta is going to be, it looks like 90 plus 30, or 2 pi over 3. So there's our theta. So we got theta and we got r. So again, you just have to be able to evaluate inverse trig functions there, evaluate trig functions, and do a little bit of arithmetic, and you're going to get r theta, which is in this case is 8, and then 2 pi over 3. again, that's going to be number 5. Alright, so make sure you know those formulas for that. Number 6, convert the polar point to a rectangular form. Now in this case we want to remember that these two formulas, and again it just comes from the same ones we use for tangent, but x equals r cos theta and y equals r sine theta, and we're just going to go ahead and use those here because, you know, why not? We got r and we got theta, so we just plug it in. So x is equal to r, which is 3, times the cosine of 2 pi over 3, and here we have 3 times the sine of 2 pi over 3. So again, in this case, we're actually using that same angle from the last problem. I'm in the second quadrant. I'm at this point, 2 pi over 3, so negative 1/2 radical 3 over 2. So again, your cosine value, so it's going to be 3 times my cosine value, which is negative 1/2, so negative 3/2. And my y value is my sine value, so that's going to be 3 times radical 3 over 2. So we have 3 radical 3 divided by 2. So at this point, that's my x, my y value, so negative 3/2, and 3 radical 3 over 2. And that is converting polar points to rectangular points. So that's number 6. Number 7, we're going to convert the polar equation to a rectangular form. So again, in this case, we want to turn the r into x and y, r and the sine theta into x and y. So again, understand all your conversions and things that we have. For one, I know that sine, again, we're just coming right up here, we're basically using the same equation, y equals r sine theta. Well, again, we just have sine here, so if r sine theta equals y, then what I can do is I can say sine of theta is equal to y over r, and then we can take that and plug it in here for sine. So we have r equals 3 times y over r. Again, notice what I'm doing is I'm getting rid of my trig function, and now I have a y value. Now the next piece that we want to know that r squared is equal to x squared plus y squared, which comes from the equation r equals the square root of x squared plus y squared. So to get that, we need to multiply both sides by r. So we have r squared equals 3y. R squared is x squared plus y squared. And we need to just go ahead and put that in standard form if need be. So that's going to be x squared plus y squared minus 3y. Right now that equals 0. I just moved the 3y over. So we're going to complete the square here to put it into standard form. So in order to do that, that's going to be equal to b over 2, which is 3 over 2 quantity squared. I'm going to add that to both sides of the equation. So this would be 9/4, and this would be 9/4 added to the right hand side. So to kind of wrap this one up here, I'm going to come up to the top, and I now have x squared. This is now in factored form, y minus 3/2 quantity squared equals 9/4. So if you look at that, that is a circle. Just shift it over a little bit, and there we go. That is your standard form, and we're good to go on number 7. It's now in rectangular form. Number 8, convert the rectangular equation to polar form. So in this case, we're using the same equations, we're just kind of using them backwards, because remember, r squared is equal to x squared plus y squared. Well, look at that. I have x squared plus y squared. So I'm going to go ahead and call that r squared. And remember that we had, for x, we have an equation that's for x. We have r cos theta is equal to x. So, in this case, I can take my x, and I can call it, in this scenario, 2 times r cos, I'll just do it this way. So 2 times r cos theta. So that's basically 2r cos theta. And now we have it in terms of r and theta. Now, if you're solving this, we want to make sure it is solved for r. So we want r equals. So I'm just going to go ahead and divide both sides by r. And that'll make it a polar equation. Try to remember, it's like when you type it into your calculator, remember it's r equals. We want r equals. So this is now r equals 2 cos theta. And again, that is your rectangular equation converted into polar form. So next up are the ones we definitely be using a graphing calculator for. So in this case, I'm going to go ahead and get it out. Now, in a way, you should know how many petals, and I'll just kind of show you the petals as I go through these and talk about the rules. But again, as we're checking these things out, you know, if you have your polar form, obviously make sure you're in polar form. And you have to understand the windows for these as well. But you're going to go 2 cosine 2 theta. So if I'm graphing that, you will probably, I don't know if my window's good, we'll see. Oops. Yeah, my window's not good, but I can adjust it so that I can see everything here. You can start to see it, and you'll see again that you have 4 petals. But let's talk about the concept here. Okay, if this number, the n theta here, if that number is even, so if n is even, then your petals are going to equal 2n. So in this case, it's 2 times 2 equals 4 petals. And you can see it in your graph. Quick reminder, if n is odd, then the petals are equal to n. They're the same. So those are your 2 scenarios when you're dealing with petals. So if I was going to ask you that question, and let's say it was a no calculator question, that's really all you need to do. Okay? And then the next one, asking about an inner loop. If we have one or not, again, same thing. Let's go ahead and graph this. You have to know what an inner loop is. So this is 0.5 plus cosine of theta. And again, we have our cardioids, which, again, if you look at it, they don't have an inner loop. But the inner loops is that when you're graphing it on the polar plane, again, your graph comes up, and you're going to, again, have a inner loop, something like that in the middle. And we're trying to see if we have it. So when you graph this, notice we do have an inner loop. So if I was doing a sketch of this graph, again, it would just be coming up, coming through 0, 0. It loops around, and it comes back through. So yes, it has an inner loop. Okay, and that, as you can see, is all the polar parametric equations. These are all the types of questions you have to know for your exam.